Welcome back. We are going to be looking at the 2.3 notes, at least the first part of it. We will be dividing up 2.3 into multiple sections here. And what we're going to be looking at is how can you compute limits analytically? Not super sure whether or not you've heard that phrase before, but basically we looked yesterday about how do you evaluate a limit if you have a graph. Analytically would mean by looking at the equation and doing an analysis of the actual equation. And most commonly, we'll be using a lot of algebraic approaches. Wow, that pen did awesome. Let me retry a different one, which is also doing great. But really, this is an algebraic approach primarily. Okay, so we're going to be noticing that a lot of the functions we'll be working at are continuous. And what we mean by that is that if you trace along the path of a continuous function, what will happen is you can do so without ever having to lift up your pencil. And so we consider those to be well behaved and very easy for us to evaluate a limit as long as we stay within the domain of that function. And the strategy that we'll use is by substituting in a value, and the value will be the one that x is approaching. That works great for constant functions, something like y equals 4. For polynomial functions, something like y is equal to negative 5x to the fourth plus 3x squared. Rational functions, something like y equals 1 over x. We do have to watch for those domain restrictions. Radical functions like y is equal to the square root of x. Again, we're going to watch for domain restrictions. And trig functions like y equals sine of 2x and so forth. We can also use composition functions made up of these other well-behaved functions. So if you're dealing with these types of functions, including a composition of them, then you can use substitution. In fact, substitution is going to be your main strategy. And it's really the strategy that you want to look at as your kind of your go-to as your first strategy. If you already have a graph, then you would use the graph. But without having a graph for some of these functions, some of them would be really time-consuming to figure out what the graph looks like, and so we will use substitution instead. All right, in this particular function, I'm just going to go ahead and replace x with 16. So as I evaluate this limit, one of the things that happens on the AP exam is that notation starts to become problematic for students. Sometimes they have really great methods and strategies, but their notation is poor, and they end up getting themselves in trouble and losing points. Limits is one of the topics where notation can cause a problem. And so what I end up doing with limits is I draw a lot of arrows rather than equal signs. I'm going to explain a little bit at a different lesson why I do that, but it's a good habit to just get into to not have notational problems. So what I'm going to do is I'm going to just take this expression, I'm going to rewrite it, and I'm going to substitute in, instead of x, I'll substitute in 16. And then I'm going to evaluate this. If, when I evaluate using substitution, I get a numerical answer that doesn't have any problems, such as a 0 on a denominator would be problematic, but if I don't have something like that, then I can go ahead and use the answer that I get as the evaluation of that limit. So this would be 12 times square root of 16 is 4, 4 minus 3 is 1 over 7. So this would become 12 sevenths. And that's the answer for number 1. So why don't you take a minute, try number 2 and 3. You can pause this video, and as you are ready, you can go ahead and restart the video and see how you did. All right, so I'm going to go ahead and do this next problem. You might notice that I'm going to replace x with 3 because trig functions are, over their domain, are continuous functions and are well behaved. So in case you have forgotten a little bit, with your unit circle, 3 pi over 2 is down here. Sine is going to be, for this point, the y coordinate. And so the sine of 3 pi over 2 is negative 1. And so the limit here is negative 1 as well. Number 3, I'm going to replace that negative 2 in for x, substitute in negative 2 for x, and so I have the cube root of negative 1, which simplifies to negative 1. You do need to simplify all radical expressions as you go throughout calculus. All right, here's this next one. We're going to take a look at this function. F of x is equal to x squared minus 3x plus 2 over x minus 1, which is a rational function, which was on our list of well-behaved functions as long as we are really looking at just staying in their domain. And we want to go ahead and see what happens if we try to find this limit by using substitution, by using graphs. So we have to think about what this looks like, and also some other analytical manipulations. And so we'll see what else we can come up with. I'm going to start with substitution. So if I'm trying to find the limit here, I'm going to go ahead and replace x with 1. You might already anticipate a problem before you get too far on this, because you might notice that 1's not actually in the domain here. But this is still worth us looking at because it's going to help us, I think, understand some notation and some conclusions we should and should not draw. If I simplify this, I end up with 0 over 0, which is very commonly misinterpreted initially by students. When people see 0 over 0, they tend to think that means undefined. Well, when we're looking at limits, 0 over 0 does not mean undefined. What 0 over 0 means is it means indeterminate. Indeterminate. Well, determinate means you can figure something out. You can determine it. You can make a decision. The prefix in means not. And so indeterminate means you cannot make a decision. Basically, what this means is that there's not enough information. We cannot make a decision about what this means. We are going to need a different strategy in order to make this decision. So when you see 0 over 0, please do not stop and think, oh, does not exist, I'm just done with the problem. That's not actually true. That's an indeterminate form, meaning you cannot draw a conclusion. We're going to have to look at this differently. I'm actually going to do part C before I do part B, because the strategy I would use graphically would actually start with me doing some analytical manipulation of this. So what I'm going to do is I'm going to take f of x and I'm going to rewrite this in a factored form on that numerator and see if I can get an equivalent version of this expression. So if I factor this as x minus 2 times x minus 1 over the quantity x minus 1, we can see there's a repeat factor. And so this is equivalent to the expression x minus 2. So although I could not use substitution with the original form of f of x, if I simplify this down and reduce out the repeated factor, which is going to indicate a hole on the graph, then I could say, hey, this is going to be equivalent to x minus 2. And so I'm going to do the limit as x approaches 1 of the expression x minus 2. And I am again going to use substitution, but I just went through first and rewrote this in a different form through factoring and reducing. And what I can find out with, oh boy, that's hard to do correctly evidently, is that this limit actually is equal to negative 1. So the height that's being approached here is negative 1. And it is very helpful to take a look at this graphically. And if I were graphing this, I would really go back to this process right here. And to recognize that what this is this is the line y equals x minus 2, which I do know how to graph. It has been a while since we've been in school, but that's how we graph the line y equals x minus 2. However, we did have this hole that was showing up through this factor, and the root or the solution of the factor x minus 1 is 1. And what this really is telling us is that there is a hole in the graph right here where x is equal to 1. So there's a hole right there in the graph. Having trouble. We'll try again. And so this is actually graphically what f of x looks like. So if I were starting with the graph, then doing the limit here is not hard, because the limit as x approaches 1, if I look from both the left and the right to see what height I'm approaching that height of negative 1. which matches, by the way, what I got through my analytical method of factoring and reducing down to a simpler expression that would be equivalent. And so I don't want to just stop at that 0 over 0. You might notice the answer here is not that the limit doesn't exist. The limit is -1. 0 over 0 is an indeterminate form, and we should not make a conclusion out of it. I'm going to move on to the next page. And let's say we're just going to kind of look at this expression here. Let's C is some constant. It's going to be a real number. And we have these two functions, f of x and g of x, and they are equal to each other for all values except not at C in some open interval containing C. All right, so we're looking in between two values. Maybe we can call some numbers a and b, and C is somewhere between them. Okay, so C is somewhere between these values, and we're looking at it at a graph. If the limit as x approaches C of g of x exists, then the limit as x approaches C of f of x is the same value. And basically the idea of that is kind of what we used when we were simplifying this expression right here. We simplified the expression of f of x into an expression that's equivalent everywhere except for not at this domain restriction. This is our C. And so if we use the simpler expression, I can go ahead and use that as the limit for f of x. And so that's basically what this right here is saying. So there are a couple different strategies that are going to be more commonly shown up. There actually are more than just these, but these are the ones that you'll be using the most. The first one is to rewrite the function so that the undefined value is reduced out. Usually that's through factoring. You can also simplify really complex fractions by getting a common denominator. The second strategy is unusual. It's to rationalize the numerator, which can be surprising. You have some experience rationalizing denominators, but rationalizing a numerator may not be something that you would